Our first speaker today is probably very well known to a lot of you. He's a regular guest at the Perspectives. It's Professor Michael Murtaugh. He's professor at the University of Minnesota in the Department of Veterinary, and I can never remember the full title of the department. He's the head of graduate studies there at the university, and he's been a full professor since 1995. He did his bachelor's degree from Notre Dame and his PhD from Ohio State University. And I learned today that he did it in entomology. So if you have any insect questions, Professor Murtaugh is your man. He also told me that he likes to work cutting wood as his hobby. So, but the majority of his time he spends doing high-value research on PRRS, focusing particularly on the immune response and the pathogenesis of PRRS virus. So without further ado, let me introduce you to Professor Michael Murtaugh. So hopefully, I did what I didn't have to do. Sorry, Mike. I can't believe it. The mouse doesn't. I couldn't control the mouse. The mouse wouldn't appear on the screen. There we go. Good.
Good morning. It is an honor to speak to the Chinese and Asian pig industry about the issues around immunity to PRRS virus and the implications that that has for making vaccines to protect pigs against PRRS. And the work I'm going to talk to you about today is an important issue, and we try and bring the best minds from around the world to help us. And we see here some of the collaborators that have assisted us in the information I'm going to provide. And you can see from the list of sponsors the people and the groups and the governments that think that this is an important issue. There are 4 questions that I want to address here. The first is, what is the virus that we are dealing with, particularly in Asia? We need to know and appreciate how diverse this virus is. On the immunological side, we need to understand what the essential characteristics are of vaccines which provide protection. So we'll look at what elements you have to have. Second is the importance of cross-protection. There's a tremendous diversity of PRRS viruses, and vaccines are made against a single isolate or a single protein, so they must be able to cross-protect. And third, what are some of the immunological challenges and the approaches that we take trying to understand mechanisms of immunity to help us understand how to work towards better vaccines. Okay. The first point that we want to make is that PRRS virus is a genetically tremendously diverse group of viruses. So what we are looking at here is the type 1 viruses, which were first discovered in Europe on the left side of this analysis of genetic diversity based on ORF5. And on the right side are the type 2 viruses, which were first discovered in North America. And within type 2, the diversity we see is more than 20% from the most different PRRS virus sequences, and it's similar in the type 1 viruses. These 2 groups of viruses are quite different, and much of that information is shown here. Type 2 viruses grow to higher levels in pigs than type 1 viruses. Type 2 viruses cause severe respiratory disease in growing pigs. Highly virulent strains like the high-path PRRS in China kill pigs. Type 1 viruses cause little or no respiratory disease. In Europe, where these viruses predominate, European producers basically do not consider respiratory disease to be an important PRRS problem. Reproductive disease, type 2 viruses, severe reproductive disease, highly virulent strains kill sows. Type 1 virus causes abortions, weak-born pigs, rarely if ever kill sows. It is less virulent. Type 2 viruses grow readily on a cell culture line commonly used to isolate PRRS viruses. Type 1 viruses grow very poorly, so it can be difficult using classic virological methods to isolate type 1 viruses. But importantly, the evolution rate, the rate of change of both of these viruses is very high. That is one reason why we see such tremendous genetic diversity. Again, I want to emphasize that the type 2 viruses are the major, if not only, key type of disease-causing PRRS virus in Asia. There are occasional reports of type 1 viruses, but in terms of immunological protection against PRRS virus, the critical issue is to get protection against type 2 viruses. One of the challenges then with respect to immunological control of PRRS viruses is not only the genetic diversity of those, which is shown in this dendrogram, but we also see more virulent strains arising on a regular basis. In 1996, there was a so-called abortion storm type of virus which appeared in the US. In 2001, another more virulent group of viruses, which we call 184 viruses, appeared in Minnesota. The high-path PRRS appeared in China in 2006. Another class of virulent viruses in the US in 2007. Who knows what might appear next year? Important point here is you see that these new viruses are not unusual forms of PRRS virus. They are arising out of well-described classic type 2 virus families wherever they appear. So the immunological controls are not that challenging from the perspective that these are regular PRRS virus isolates. The second problem in dealing with the diversity of PRRS virus is that the humans are spreading PRRS virus around through the movement of pigs or pig products such as contaminated semen. In China, high-path PRRS first appeared in April of 2006, and within 3 months had spread to 13 different provinces. This could only have happened by infected pigs or contaminated semen being moved around in China. So this movement of virus through the movement of infected pigs is an important consideration in efforts to control the virus. The second example shown on the right side is from an analysis of PRRS virus sequences in Japan, where sequences were described in 2008. Shown on the top of this dendrogram that had been previously described the year before in the United States as a new strain of viruses we call 118.2. And these viruses somehow within 1 year had appeared in Japan, despite what is assumed to be strict controls over importation and movement of pigs. So it's very clear that PRRS virus is being assisted by humans in its distribution around Asia. So we need to understand in discussing immunity and vaccinology to PRRS virus that we need to concentrate on type 2 viruses, that this is a very genetically diverse group of viruses, and that we need to pay attention to the potential role of humans and pig transportation and movement in the problem. Now, in considering immunity to PRRS and the use of immunological principles to make vaccines, the first question that comes to mind in how good a vaccine can you make is vaccines depend on the pig's immune system to resist virus infection or cure an infected pig. So the best vaccine will only work as well as the pig's immune system works. So we need to know if a pig can completely get rid of PRRS virus. If it can, that means that our goal for vaccinology is complete protection. And veterinarians in the United States developed a method for getting rid of PRRS in large sow herds by this method called herd closure. And in herd closure, you pack a sow barn full of pigs, you generate homogeneous immunity through the entire herd by directly exposing all of the pigs to PRRS virus. Then you close the herd for a long period of time so no susceptible animals are introduced. During this time, you allow the pig's immune system to clear the virus infection. And you know you got rid of the virus if after a long period of time you bring new pigs in and they do not become infected. And this method works very reproducibly. This means then that the pig's immune system is able to completely eliminate PRRS virus. So it tells us that we should be able to develop vaccines that are completely effective. The second thing is you see that this takes a long period of time. Early on, it took more than 200 days. Highly virulent isolates in the US today, it often takes more than 300 days. So it takes a long time. One goal of a good vaccine would be to shorten that period of time in which you can get effective immunity. And remember, these vaccines will need to cross-protect against a total diversity of type 2 viruses. Vaccination also is clearly demonstrated to be effective in the field. So in this example, we're looking at a nursery that is suffering a high rate of death loss for more than 2 years' time, where shrinkage refers to loss of pigs from the time you filled the nursery to the time they move on to the finisher. A vaccine was introduced at the point of the blue arrow, and immediately following that, and for 2 years afterwards, you can see a dramatic reduction in death loss in the nursery, demonstrating cross-protective immunity endowed in the pigs by the vaccine against the virulent field isolate that was in the herd. Okay. This cross-protection is real and easy to demonstrate in controlled experiments. And this example, taken from a study done at Iowa State University, shows in lines 4, 5, and 6 that 3 different virulent PRRS viruses induced severe clinical signs in infected pigs. And the lung lesions were on the order of 20 to 50% involvement, severe disease. But in the 3 lines above, you can see if the pigs were vaccinated first with a vaccine virus that was substantially different from the challenge viruses, high levels of protection. So a 10-fold reduction in lung lesions, that is definitely protection. Second point, though, is that you can see it is not perfect. because totally uninfected pigs in the bottom showed almost no lung lesions whatsoever. So again, first of all, vaccines provide protection against PRRS. It's cross-protective, and it is not perfect. Again, this cross-protection can be easily demonstrated under a variety of conditions. Here we are looking at a series of challenge studies carried out by Boehringer Ingelheim. So pigs were vaccinated with 2 different kinds of live attenuated vaccines. A period of days from 21 to 180 elapsed, and then pigs were challenged with one of a number of different challenge isolates. And we can see in every case that the lung lesions of non-vaccinated pigs was more severe than vaccinated pigs. Sometimes it was a gigantic effect, other times it was a smaller effect, but in every case, all of these cross-protection studies showed a significant benefit of vaccine. So again, vaccines protect against PRRS, they provide cross-protection, and there is room for improvement. Okay. So far, we have only used examples taken from studies done in the United States with United States isolates. Here is an example looking to see if vaccine protects against high-path PRRS, a study done by Shishan Yuan when he was at the Shanghai Veterinary Research Institute. We see that in the first line that pigs that only were challenged with high-path PRRS suffered high mortality. Only 4 out of 12 animals survived challenge, and they were characterized by having a high fever for a long duration of time, 3.5 days. Pigs that were vaccinated first and then challenged had reduced fever at a reduced temperature and no death loss, significant difference. We see on the bottom left the survival curve, which showed that these animals that died were within a window of about 8 to 14 days. This is a classic characteristic of high-path PRRS, something that is seen nowhere else in the world, where pigs die within nearly 1 week of infection. And those pigs that died on the right, we see, had high clinical scores for a long period of time. And the benefit of vaccination is clearly demonstrated in that the peak of clinical signs was reduced and the duration of clinical signs was much less. So one of the reasons that vaccines prevent death by high-path PRRS is that they reduce the severity of disease. Okay. So I have emphasized so far that vaccines work against PRRS. They consistently provide cross-protection, but they are not perfect. And this issue of being perfect is an important one to consider. So we have looked to see how good can PRRS vaccines be against current virulent field isolates. Are vaccines not that good, or is the ability to protect pigs against virulent isolates not perfect? So here we did an experiment with a Minnesota veterinarian that mimics what happens in sow farms in the US. So young gilts were inoculated with a virulent field isolate. A long period of time, more than 200 days, was allowed, during which these animals were bred, and then they were challenged in late gestation, which is the most sensitive time of PRRS virus infection. And we looked to see if the sows got sick. We looked to see what the reproductive performance was, and we looked to see if the pigs weaned from these sows were viremic. Critical issue in the US is weaning negative pigs. So if pigs are positive at weaning, that's a very bad sign. To our surprise, we found in the results if the challenge strain was the same virus that the pigs were immunized with, a completely homologous challenge, we still saw fever, we still saw some sow abortions, we still saw a high rate of death loss in the piglets. Only 55% of conceived pigs survived to weaning. The other pigs were stillborn or mummies or weak-born that died during farrowing. Okay. And we saw significant pigs weaned viremic. And in every litter, there was at least one viremic pig. We had a second group which was challenged with a nearly identical isolate, and you can see again similar findings. So it's clear that with these highly virulent isolates we have today, it's difficult to achieve 100% protection. So again, that's a challenge for people who want to make vaccines. And it also says we need to understand what the mechanisms are so we can target what the key properties of a good vaccine are. Okay. So let's look for a minute at what's needed in a vaccine that provides good protection. And here, we're going to concentrate on a simple question, because all of the vaccine data I have shown you up to now is based on live replicating viruses. So field viruses taken into the lab and attenuated, but they still replicate. So, do you have to be replicating, or can you be a non-replicating product, such as a killed vaccine, similar to some products sold now in Asia and in North America? And this is one of about 2 studies I will share with you. This one done again at Iowa State University, in a model of how vaccines are often used in the field. There's an outbreak, you rush in with the vaccine to try and calm down the outbreak. And here they used killed vaccine at 7 and 21 days or 14 and 28 days, and then they measured their outcomes a little later. And the key statement is the sentence that's highlighted, where you can see that the magnitude and duration of viremia in the killed virus vaccinated pigs was the same as in the non-protected pigs. So there was no efficacy to the killed vaccine. So the conclusion from this study would be that for protection, you need replicating virus. And what's not clearly stated in this study is this was a homologous challenge, not heterologous. So even in the perfect situation, the killed vaccine did not protect. A second study is summarized in the title of this published paper from an Italian group looking at type 1 viruses, where again they were looking to see if an inactivated vaccine would provide protection against reproductive disease in a sow herd. And they found no evidence of protection in a heterologous situation. So again, I conclude from this that you need replicating virus as a property of an effective vaccine. In addition to whole virus vaccines, we want to use the power of genetic engineering and molecular biology to take key immunogenic portions of PRRS virus and use those in subunit vaccines or vectored vaccines to provide protection. And some of those products are available in the US. Here is a study looking at the results of a reproductive challenge model, where the red bar is what happens if you infect a pig with the virulent virus. The yellow and green bars are what happens if these pigs before challenge are vaccinated with these products, and the dark blue bars are a live attenuated vaccine. And you can see on the left side that the direct disease in sows measured by viremia at 8 days was high with the virulent challenge virus, was still high in those with the subunit or vectored vaccine products, but the live attenuated vaccine, there was no viremia at 8 days. In the next two sets of data, if you look at piglets that failed to wean, in other words, mortality prior to weaning, and if the piglets were viremic, PCR positive at weaning, again, we see high rates in challenge only. We also see high rates in the non-replicating products, and we see that the replicating vaccine substantially reduced those bad effects. Not completely, but a substantial benefit. And on the right side, we're looking at a measure of illness. Sows off feed, they're too sick to feed, and eating is one of the things that pigs are very good at. We can see that the challenge by itself did not make these pigs so sick that they stopped eating. They continued to eat. But if they received the non-replicating second-generation products, they went off feed, suggesting something worse than just PRRS by itself. And again, vaccine reduced illness enough that there was no negative effect on feeding. Okay. This observation that non-viral parts of PRRS virus, as a subunit vaccine, for example, might actually make disease worse has been observed previously. One of those is shown here, a study done in Spain by Cinta Prieto, where the title of the paper is The Conclusion: Immunization with the envelope glycoprotein as a subunit product resulted in enhanced clinical disease following challenge. Second, we saw this previously ourselves. And here, the point of this experiment was to see if we could make a live replicating vaccine work better. How do you get from 90% efficacy to 100%? Can you do it with adjuvants? Can you do it with potentiating the antibody response to envelope glycoprotein, and so on? So we see challenge alone near the bottom, about 35% clinical signs, large number of animals with significant lung lesions. At the top, MLV, substantial reduction in clinical signs, substantial reduction in pigs with severe disease. We saw a number of products which did about the same, but the two outlined groups that had envelope glycoprotein 5, GP5, supplemented as a boost. So you vaccinate with your live attenuated virus, you inject with booster shots of envelope glycoprotein 5 or a key peptide with a powerful adjuvant cholera toxin, CT. You can see in these two groups disease was worse, raising great concerns about the use of vaccines that are something different from live replicating virus. I also would like to point out there's an issue of whether PRRS virus is immunosuppressive or does not induce an innate immune response. This experiment also addresses that point. In groups in the middle, we had groups that were given interferon alpha, an extremely expensive adjuvant, or an inducer of interferon alpha called poly-ICLC, or a potent cytokine called IL-12. None of these enhanced the effect of live replicating virus by itself, suggesting that the vaccine is providing a high level of protection and is stimulating all of the elements of an immune system that are necessary to get a robust immune response. Okay. This slide is important in a practical sense for three reasons. The first point that this slide shows is that attenuated replicating vaccines grow to a lower level in pigs than virulent virus. So weaned virulent and sow virulent show the levels of virus growth in 2 different ages of pigs. Weaned vaccine and sow vaccine shows that the vaccine levels in matched controls grows much less well. Okay, so this is why these vaccines provide immunity but do not cause disease. The second point is, and has not really been clearly demonstrated before, that older animals have innate intrinsic resistance to PRRS virus growth. You see that in both cases, that virus grows less well in sows compared to young weaned pigs, and the duration of viremia is much reduced. So to me, there's an important point here that if you're using live replicating vaccines in sow herds to get effective immunity on a consistent basis, it's wise to use whole doses of the products. If you start cutting the doses and giving lower levels of infection, you raise the possibility that the immunity will not be as complete, and this is an important issue for cross protection. Okay. So the previous slides, to me, really make a compelling case for the need to get good immunity to PRRS. As best as we know today, requires that you need to use an intact PRRS virus, and it needs to be able to grow in a pig. But in terms of making better vaccines for the future, we want to know what the mechanisms of immunity are. Classic immunology says that antigen-specific immunity is an inherent property of neutralizing antibodies and T-cell immunity. So let's look and see how that works out with PRRS virus. What we show here is a standard time course of viremia following virulent infection. We can see that it peaks at about 7 days. It goes down rapidly, so something in the pig is controlling this viremia, and the pigs go non-viremic at about 35 days. So the period from 35 days on, these pigs show no viremia, it's only in the lymphoid tissues. What is controlling viremia? Well, it is not neutralizing antibodies. These first appeared only at day 42. This is a homologous immunity example. The following slide shows a heterologous immunity example from a study done by Kim et al. A few years ago in Korea. What is shown on the y-axis on their left side are pigs infected with different PRRS virus isolates. Those pigs made antibodies to those viruses, so they have serum. The serums from those pigs were tested against the same viruses shown on the x-axis for cross-neutralizing antibodies. The black bars show homologous antibodies, so serum tested against the same virus that the pigs were infected with. We see variable homologous neutralizing antibody responses, in some cases none at all. The cross-protective neutralizing antibodies, there are essentially none at all. And you have to remember now that vaccines only work by cross-protection. So again, the previous slide and this slide suggest that neutralizing antibodies are not essential for protection. They could play a role, but in these models of respiratory disease in young pigs, neutralizing antibodies do not appear to be necessary. If it's not neutralizing antibodies, perhaps it's T-cell mediated immunity. We think that this is very important in PRRS, but finding scientific evidence for this has been hard to produce. Here we assume that if T-cells were important, if we looked in a piece of tissue with PRRS virus, lymphoid tissue or spleen or lung, that there would be a correlation between the T cell response to PRRS and the amount of virus. So at acute infection at 19 days, we show the level of virus in individual tissue samples, and on the y-axis, we show the T cell response by interferon gamma production. And clearly, there is no correlation whatsoever. Well, maybe that's too early. Maybe we look in persistent infection. Viremia has been resolved. On the right side, we do that. Again, no correlation whatsoever. And this is in homologous protection. So it's been difficult. Is it possible that T cells have no role and neutralizing antibody is not important? Well, we do not really think so. Is it possible that we cannot measure the effective agent with T cells? That's possible. Our tools for doing T cell work in the pig are primitive. And to the scientists in the audience, I challenge you to develop antigen-specific methods for studying T cell immunity in the pig to everything, all of its pathogens, including PRRS, because that's a major obstacle to understanding mechanisms of immunity in the pig today. Okay. So we've seen that a challenge to us in developing immune responses, good immunity to PRRS, is the genetic variation in the virus itself. We've seen that you can get good immunity in the pigs, but we do not understand what the mechanisms are. And there's one more variable that has not been addressed yet, and that's genetic variation in the pigs themselves. And this figure emphasizes how dramatic that variation can be. So here we are looking at 7 different groups of pigs, 70 pigs taken together, randomly put into groups. And then each group was infected with a different virus from low virulent to high virulent. And the numbers in each column are the lung lesion scores from each pig in the group. And in group 1, we see this was a very low virulent virus, little or no lung lesions in most of the pigs. But 2 of those pigs had substantial lung lesions. One pig, more than half lung involvement. If we move over, say, to group 4, we can see with these high percentage numbers that this was a highly pathogenic virus. 1 pig died in the course of the study, yet we had 3 pigs with insignificant disease. Same virus in every pig, same housing, same management. The only difference is the pig. There's tremendous variation among pigs in how they respond to PRRS virus. We have no idea what's responsible for this, but if we can understand what it is, then it will allow us, give us much better information and allow us to develop better tools that might depend not only on the virus, but on the pig itself. Okay. So what are the take-home messages from this presentation? First of all, so what is PRRS virus? What's the importance of PRRS virus to you as veterinarians and producers in Asia? It's the type 2 viruses are the viruses which are responsible for significant disease problems in Asia. The vast majority of outbreaks are due to type 2 viruses. The severe disease losses are due to type 2 viruses, and this needs to be the focus of attention in developing good immunity and developing good vaccines. What do we need to generate good anti-PRRS virus immunity? We clearly need live replicating virus to get protection. There will be a day in the future when we figure out what about this live replicating virus is really important. But today we do not know. So the minimum now to get reliable protection is live replicating virus. How good is the cross protection that these viruses produce? And remember, these viruses in current vaccines are a single isolate, usually taken from the field years ago. That sequence usually is no longer present, so they can only work if they provide cross-protection. And we've seen under many different conditions that live replicating viruses consistently produce cross-protective immunity to some degree. Very high levels in some cases, less high levels in other cases. So what are the challenges then to achieve the goal of complete cross-protection in all situations? We need to determine what the mechanisms of protection are. What is the role of neutralizing antibodies? Do they work in some ages of pigs and not others? Are there some pigs that are better able to make neutralizing antibodies than others? Some of you in the audience know that antibodies have other functions besides neutralization. Perhaps one of these other functions is more important. We need to find out. What is the role of T-cell immunity? Everything that's ever been learned about in immunology, about protection against disease, says that antigen-specific T-cells have an important role to play, regions and so on. We need to be able to manage the variation by understanding what the determinants of cross-protective immunity are in the virus. And last, we need to understand variation in the pig. Again, this is unrealized. We need to understand what it's due to, and then we need to incorporate that knowledge into our vaccine development programs. And so while we have many challenges facing us, I'm confident that we will be able to make progress moving forward. Thank you. Shishi.